Hi everyone, I'm here to introduce today's speaker. Today's speaker is Heather Hunter. Heather is a 5th year PhD candidate in the AMP program working under Hans Graber. A fun fact about Heather is that she has a cat named Kepler. And today she'll be talking about deep learning for object detection in satellite-based synthetic aperture radar imagery.
Thank you, Joe. Good afternoon, everyone online and everyone here. So as Joe said, I will be talking about the work I've done towards deep learning for object detection in satellite-based synthetic aperture radar imagery. So this is a brief outline of what I'll be talking about today. I'll be giving an introduction and then talking about a few approaches we've taken, including transfer learning, object detection, domain adaptation, and then I'll give my conclusion and some future work to be done. So what exactly is object detection? Well, the textbook definition is that it's a process related to computer vision and image processing that deals with detecting instances of a certain class. And there are many domains, many of which are pervasive in your lives already, like facial recognition, pedestrian detection, and other kinds of car crash avoidance technology. So these kinds of algorithms are in your cars already. But we're not interested in that. We're interested in satellite imagery. So what exactly is it used for in satellite imagery? Well, primarily for monitoring the environment. So we're interested in detecting and tracking icebergs, sea ice, oil spills, and other kinds of natural hazards like fires, like out in California, as well as earthquakes. Then traffic monitoring is also very important. So monitoring maritime traffic, looking for ships that are not supposed to be where they are. Then also road traffic, looking at density, population densities and traffic density, and then looking at planes and being able to detect aircraft density. Finally, another important application is urban infrastructure monitoring. So for example, with the fires out in California, we might be interested in where are there no longer homes where there used to be homes. So monitoring that change. So some of the conventional methods that have been used both in computer vision and in satellite imagery are methods that rely on feature engineering. So whether you're looking at gradients or you're looking at other kinds of features, there's a lot of work that has to be done before you can even run the object detection algorithm to decide how do I best identify an iceberg or how do I best identify a ship? What are the features that really determine what those things are in a feature space? And then one of the machine learning algorithms that also relies on feature engineering are support vector machines. And so the shortcomings of all of these, even though they're powerful and they do work in most instances, just is that it requires careful engineering for selection of features. And detection is multi-step, so it involves this feature extraction, object classification, and object localization. And this really, it isn't a technical problem, but it is a problem in the sense that we now have more data than ever. So we're sort of in this era of what people like to call big data. We have better technology, we can get higher resolutions, and we can collect more data than ever before. So that begs the question, can we learn from the data itself? And the answer is yes, especially with deep learning. And for imagery, we look mostly at using convolutional neural networks. And I like to think of CNN simply as a stack of image filters. So the convolution part is in image processing, you would take an image and then you would take a filter, say an edge detection filter, and you perform a convolution operation between the two. And that extracts the edges from the image that you're interested in. So CNNs are based off of multi-layer perceptrons or neural networks. And essentially that means it's stacks of these neurons that have some kind of weight and bias, some parameters that can be tuned. And so the CNN and other deep learning algorithms can learn a hierarchy of features. So At the top layers, you have your edges, and then the features become more complicated as you go further down, until eventually you can detect faces. So in the case of President of the United States, then you can classify George Washington. This is great, but it requires a lot of training examples. And satellite data is different primarily because you can't rely on the pre-existing networks that come off the shelf, the state-of-the-art computer vision architectures. It's not that simple because when you look at a photograph, for example, of a ship and a satellite image of a ship from overhead, the orientation angle of the ship relative to the sensor is completely different. So there's likely to be some kind of difficulty in the algorithm understanding that these two things are the same. And then we further complicate things with synthetic aperture radar. So whereas optical images, optical sensors rely on solar illumination, a synthetic aperture radar has a directed signal that goes towards the image seen with some wavelength and polarization. And it's in the radio portion of the electromagnetic spectrum. And it reads, or it collects the backscattered signal and then creates an image out of it. Well, this then means that we're dependent on the look angle. We're dependent on the incidence angle, which is the angle between the signal and whatever object you're interested in, which can change depending on which object you're looking at and how it's oriented towards the sensor. And then furthermore, it's also the signal and the image are dependent on the electric permittivity of the image seen. So for example, let's say you're looking at a city in a desert. So the desert is dry, and since there's very low moisture, the signal gets absorbed, most of the signal gets absorbed into the ground, and then the rest of it's scattered. Well, if there's snow for some reason, then it's all going to get reflected. That signal will get reflected. Whereas if you have flooding, then the signal gets specularly reflected off of that surface. So you have backscatter that is highly dependent on the SAR target geometry, and then you can have variable ground surface scattering. And so this means there's so many different combinations of images that you might need for deep learning. And unlike computer vision, we don't have large-scale benchmark data sets, and we don't have pre-trained algorithms. So I can't go to like PyTorch and download a model that's ready to go for SAR. So there's a couple things we can try to do about this data problem. One of them is data augmentation. So that just means applying some affine transformations, adjusting the hue, saturation, and brightness, adding noise. And these are things that you should be doing regardless, but especially when you don't have a lot of data. Then there's transfer learning, which is the subset of machine learning, where the idea is if you have similar imaging domains or any similar kinds of, if the images have similar distributions, then you can use it for different tasks. So if you're trying to, say, classify tigers and then classify cats, you can transfer the features that were learned in one domain and then transfer them to the other. But how effective is this for remote sensing and especially for SAR? This is a brand new kind of question that people have been starting to ask within the last decade. And then domain adaptation is another possible solution. So unlike transfer learning, we're not just trying to take features that we've already learned. We're trying to create a whole new feature space that will work on both domains. So sorry, I'm kind of rough. The three main research objectives of this entire talk that I'll be discussing, the first is leveraging features learned in other domains through transfer learning. And then looking at modeling a domain invariant feature space, and then using these models for a deep learning-based object detector. So the first thing we'll look at is transfer learning for multiple domains. So to recap, there's not enough training data for satellite remote sensing. There are no pre-trained SAR networks to start from, and it's not really addressed much in the literature except for optical. So the two main questions we're trying to answer are, is transfer learning from ImageNet effective, and can simulated data help? So first, we have to choose a model architecture. There are 3 that we picked. AlexNet was one of the first state-of-the-art convolutional neural networks from, I think, 2012. And it's a shallow architecture, which means it doesn't have that many convolutional layers. So it's really not too complex, and it doesn't, it's not able to learn as rich features as the other 2. VGG16 came a few years later, and it's slightly more complex with a couple more convolutional layers, which means that it can learn slightly more rich feature domain. And then ResNet 18 is the last and more complicated of these 3. And it's both what we call a deep architecture with many, many layers, and it uses residual modules, which act sort of like an identity function. And so it's able to use information from early on in the network to make decisions later. So like I said, we're going to be doing transfer learning, and to give kind of an idea of how that works, we start out with one of those models, like AlexNet, and we need to decide which layers are we going to use. So in this case, let's say we take the first convolutional layer, the first feature layer, and these usually are edges. So we're going to take the parameters from this layer, and we're going to extract those, and then apply them to another version of AlexNet where it still has those other ImageNet parameters, but we fine-tune them with SAR. So what that means is that the first layer, we allow it to be constant. We don't change them at all. We don't let them see the SAR data. Whereas the other layers get to see the SAR data, and we let them change a little bit. So in our approach, basically, we make 4 variations of each of these 3 models where we're interested in transferring certain layers and then fine-tuning others. So for simplicity, I call them A, B, C, and D. And the idea is that, for example, model B, where we transfer the first feature layer, we're transferring edges. And then for C, we have the first few feature layers where it's basically combinations or textures. And then D, where we transfer all feature layers, which are the more complex features. So in the end, we have 12 models that we're going to run experiments on for transfer learning from ImageNet. But we also want to know, how does it work for simulated images? Will the simulated images help at all? So what we do is we start with the least complex and the most complex models. We reset the network weights and biases. So we erase all of its memory basically from what it learned on ImageNet, and we reinitialize the parameters with random values close to 0. And then we retrain these models using our simulated SAR data. But we are interested in, if we can model any kind of data we want, to what degree will it cause failure in our models? Because surely we can't just throw at it everything that we can ever create. So we start with 4 different training sets to train all these simulated architectures. So the first training set contains images modeled at incidence angles that are already in our training data set. And then I progressively add more incidence angles that are part of TerraSAR-X staring spotlight mode. And as before, I create 4 variants of the 2 models. And then as training data for SAR, I have available to me 23 TerraSAR-X images of 2 airports at 2 different incidence angles that were acquired in descending orbit, and there are 6 classes, and so we end up with 1,584 images to train them. Then for simulated images, I take an open source SAR simulator. It adapts an optical ray tracing software called POV-Ray and wraps it with MATLAB. It's fairly robust and was really designed to investigate scattering effects. So the input are the orbital parameters of TerraSAR-X, the imaging parameters like the spatial resolution, and various processing parameters, and then a CAD model, of course. So for example, we have a passenger jetliner. So this comes from Trimble's SketchUp software, and that is input into this simulator, and then what is output is an image that represents the complex amplitude of the simulated SAR signal. So here we're able to see that it has understood the height of the aircraft, and there's a shadow, and there's some layover effect, and I'll get into that more a little bit later. So what I end up with is rotational variance, which I don't have in the real data, noise variance, because I'm able to model 3 levels of noise, as well as a wide incidence angle range that covers the entire range for Terrace RX during spotlight mode. So I end up with 26,000 images, which is significant. So on to the results. So if we look back at transfer learning from ImageNet, can we use these features to classify objects in SAR images, and how does it change by incidence angle? So it's a lot of graphs, but overall, I wanted to discuss the trends. So for AlexNet, when I am taking features learned from ImageNet and transferring them to SAR, it seems that performance worsens as I add features from ImageNet. So this is actually to be expected, because I can't expect that these features that it learned on optical imagery or optical photographs are really going to help the SAR images. For VGG16, it's not the same story. It's a slightly different story, where Model C, which is where I transfer the first few layers, performs the best. And then for ResNet, it's about consistent with extremely poor performance on the third test data set, which is 41 degrees, and that is because there isn't that much data with that incidence angle in my training data. So the next results are, can we train a network on simulated SAR images and use those features to classify real images? So if we look at the variation of AlexNet that was trained on SAR simulated images, and we look at the first training set, which is exactly the same incidence angle range as the real SAR data. Again, it's consistent across the board except for Model A, which I expected to be a sort of fail. And then for the next few training sets, no matter how much data I add to it, it still poorly performs, and it's pretty consistent across all these models. For ResNet, it's about the same story. The performance is extremely poor compared to how it performed with ImageNet, and fairly consistent. So my conclusions from this work, from the transfer learning work, are that, first of all, if we want to use ImageNet to do transfer learning for the SAR classification, it depends on the architecture that we're using. So for AlexNet, it's sufficient to transfer simple features, so the top layers, like edges. Whereas for VGG16, we can transfer a few more. And then for ResNet, it's fairly consistent across all variants. And that's something that I don't really understand, but I think has something to do with the fact that it has residual modules and it's using information from earlier on in the network. And then overall, the worst performance is on the incidence angles that are not available in the training data, which is to be expected. And the best performance on the 31-degree incidence angle, because that is the training data, that is the incidence angle that's most present in my training data. So it's almost like it's overfitting to my training data. Then for the simulated images, for AlexNet, what I see is that it is responsive to additional simulated data, but adding data outside the range, like the 31 to 47.46 degree range, introduces noise. And then for ResNet, results are inconsistent, but this points to deficiency of the simulated data. So the fact that this powerful architecture performs best when I don't give it as many features from the simulated data set shows me that something's wrong in my simulated data. So this work we are preparing to put it in publication, And then the next work that we're doing is applying these networks to object detection. So unlike object classification, detection requires localization. So if we have a car that is doing object detection on the street, it needs to know not just that these are cars and trucks, it needs to be able to know exactly where they are. And usually this is a multi-stage pipeline, especially for satellite imagery. So you have to search the image space, generate candidate object proposals, refine those proposals, and then finally you can classify the object. So what we are doing is we take all of those models that I talked about, and we're going to apply them to an object detection algorithm. And there are many, many state-of-the-art algorithms to choose from, but what we chose is the faster RCNN. And all this means is that instead of doing the object proposal part and the classification part separately, it does them together. So it uses the features that it learns on the classification part to generate object proposals in the image. And it uses a slightly different training data set than what I used before. These are from different images than the ones I had before, but they're of the same airports and with the same incidence angles. So I'm looking at 168 sample images. I am limited to about 10 objects per sample image because of my GPU capabilities. And yeah, I use the same locations as before. So some of the key results from these experiments, for ImageNet, performance is fairly good for both AlexNet and ResNet, with a significant improvement with ResNet, as I expected from previous experiments. Then, using the simulated data backbone, overall ResNet has the best performance, and AlexNet just does not work. So if we focus on ResNet, we can see that the performance is very good for at least one of the incidence angles, and fairly poor for the others. As I explained before, I think that has to do with the data that is available to me. So to sort of visualize what's actually happening, this is an example of an output from using AlexNet trained on ImageNet for detection. So this is not using any of the simulated data. It's only fine-tuned using SAR data. And the confidence values are very high, but this is also only the case if is it an airplane or is it not? Similarly, in the case of ResNet, it's the same thing. It actually has higher confidence generally, but again, this is the binary detection case. In the case of looking at multiple classes, which is a slightly more complicated problem, this is the output where clearly it has missed one of the aircraft down in the corner, but it's done a very good job at looking at small aircraft, which is significant because a lot of these object detection algorithms really fail for satellite imagery when the objects they have to detect are really small. So this is a function of the layer that I selected to be the feature extraction layer. And the same thing for this image as an example. So to conclude this chapter, for binary detection where we're just looking at airplane or no airplane, ResNet 18 has the best overall performance. When we use simulated data, there are more false positives. So the performance metric, the mean average precision, goes down because even though I might get 100% accuracy detecting what I want to detect, it's also saying more things are planes than shouldn't be. For multi-class object detection, it's the same thing. And it's able to discern small objects better than the binary detection problem. So some of the important notes here are that faster RCNN, it does perform fine-tuning of the existing features. So it's not just taking the classifier and then just using those features. It fine-tunes them based on the things it learns. And finally, I worked on domain adaptation for SAR image classification. So the downside to transfer learning is that it really depends on how similar the source and target domains are. So this difference is referred to as a domain shift, and this can be unknown things, or it can be object location and pose, like the view angle, resolution. So this is a very common problem, especially in satellite imagery, if we want to be able to detect the same object in two different images where the spatial resolution is significantly different. So can we learn a domain invariant feature space between simulated data and real data? Because we still have this problem where we don't want to go and collect more SAR data for the problem. We want to be able to somehow use a small amount of real SAR data and maybe create simulated data, or have to create a whole new algorithm. So we look at two approaches. One is use what is known as correlation alignment. So all it means is that I'm taking two networks. Each of them are responsible for a different imaging domain. So source data and target data. And then they share all of their weights. So the filters they learn are exactly the same. And the way it would work then is it would learn different features for each domain, but the filters are exactly the same. And at the end, it calculates this loss, which is just the difference between the covariances of the source and the target data. So this difference indicates the distance between the two distributions. And that gives us, and if we can minimize that, then we've successfully created a feature space where it can understand both of these domains. Then there is a similar approach, which is just a weight regularization mode. And so instead of forcing the two networks to share all of their layers, you can select which ones do share and which ones do not. And then the ones that do not, you don't want their features to be too far apart. So instead of making them equal, you calculate a loss between them. So the goal here is you don't want the loss to be 0, but you want the distance between the features in the feature space to be as close as possible. So we did this by implementing it in PyTorch, using AlexNet, the most simple architecture, and then my source domain are my simulated SAR images, and my target domain are my real SAR images, with the same 6 categories as before. So a sampling of the results basically show a very, very good performance relative to all of the other experiments that I've done so far. So all layers being shared and having and calculating the coral loss gives a very high F1 score, which is another way to represent precision. Then we further break it down between incidence angles of our test data and the orbits that we use. So we have descending and ascending orbits. And across the board, we find the same kind of architecture applies for each of the classes, or each of the data. So in conclusion, what we actually did find is that this coral method outperformed the other methods. So it was very useful to have all the layers shared rather than sharing some and then not sharing others. And having one coral layer at the end and calculating it one time rather than applying it to multiple layers was also better. And there's a metric, the maximum mean discrepancy, which essentially just, it's a test to see whether or not two samples are from the same distribution. So it's like, how far apart are these data sets in feature space? And so having a value less than 0.01 is generally good. And so we were able to get as low as 3.98 times 10 to the negative third, which is extremely small, which is promising. So overall, the conclusions that I take away from all three of these sections, the first one is that transfer learning from ImageNet, it's possible for SAR, but it's architecture dependent. And then the incidence angle of the images in the training set is extremely important. We're basically overfitting to a degree. Transfer learning from synthetic SAR images is possible, but we have a deficiency in our image simulation. So it's possible that we are not properly modeling the background and the object textures required for the CNN to make decisions on the SAR objects. And then the presence of incidence angles outside the expected range also reduces performance. Too much information is a bad thing. It creates noise in the learned feature space. Then for object detection, we have higher precision with ImageNet-based backbones, and the synthetic-based backbones that I generated have a higher false positive rate. For domain adaptation, we saw that classification results exceeded those of simply doing transfer learning, which is great because domain adaptation is potentially a great solution to the data problem. So what is next is applying the classifiers developed from domain adaptation to object detection. It'd be interesting to see how that improves the detection results. And then, is there a way to make the simulated images better without getting too detailed? Because we don't want to have to make them super complicated in order to have good results in our object detection algorithms. And that is all. So thank you, and I'll take any questions.
Okay. Now I will switch my microphone on. Questions from the audience in the room? No? Questions from the online audience? Yes, Mr. Gleason, you need to unmute yourself. And I need to, oh, maybe you are unmuted. Wait a moment, my speaker is still off. Okay, now you can say something.
Is that good? Yeah?
Yes.
Okay, great. Heather, nice job. Thank you for this presentation. I enjoyed it. And Roland, thanks for putting this online. It's really nice to be able to just jump in and watch. I had a question about your accuracy metrics, how you're using F1 and the other. I didn't even follow what the other one was. But in my experience, I've always used F1 and similar things to be like a class specific or a binary metric for success, and I wasn't clear if you were using it that way as like a plain not plain threshold, or whether you were using it as some sort of class specific. You said you had 6 classes of airplanes, so do you compute? And I guess to be more specific, do you compute F1 for each class of airplane, or is it somehow aggregated or averaged, or just I don't know any more details about how you measure success?
Sorry.
Thank you.
I will mute you now while you speak. Okay.
So that's a good question. So I calculate an F1 score for each class separately, and then I take an average overall to give the values that I presented. But normally I would report the F1 score for each class.
Okay. Further questions? Now I even hear my own echo here. Anyone else wants to ask something? I don't see anybody. So maybe that's all. You had so there are 22 people online now. At the beginning it was 25, including you and me. So we had 23 people outside and 2 more here in the room. So that's quite good. Yeah, I guess that's all then. Thank you, Heather, again. Nice presentation under the circumstances, I would say. The first experiment of this kind. I did record this with my phone at the same time, and this evening I will load it up to the YouTube channel, so you can watch it there again if you want, from the perspective of the room here with with the large screen in the video and Heather at the same time.